So on Friday, we started graphing rational functions. Okay, we did example 3A, and we did example 3B, and we did example 3C. Okay. Now, one interesting thing about the example 3C that we did was the graph of a rational function can have a horizontal asymptote, but before it flattens out either below or above the horizontal asymptote, it may cross it first. And we had that situation with example 3C, okay, on the left end. Okay, the graph crossed the horizontal asymptote, then flattened out to the left. Okay. You don't have that situation with vertical asymptotes, but you can have it with horizontal asymptotes. Okay. All right. So you flip over to the next page. We'll graph this rational function.
Excuse me, would I be able to get a copy of 3.5?
You were gone both Wednesday and Friday?
I just don't have one on me.
Okay, I may have one left. You guys gotta stop selling these things on eBay.
Right.
Yeah. All right. So you know pretty much the procedure, okay? So we're going to answer these questions concerning this rational function, f of x equals x squared minus x over x plus 1. So the domain and interval notation is the denominator can't equal 0. And so we get x can't equal -1. Okay. And so in interval notation, the domain minus infinity, minus 1, parentheses, union, parentheses, minus 1 to infinity. Okay. All right. Equation of the vertical asymptote. Well, we got to make sure there are no common factors in the numerator and denominator first. So you'll notice that the numerator factors into x times x minus 1. And so there are no common factors in the numerator and denominator. So the equation of the vertical asymptote, right? You set the denominator equal to 0, solve for x, and you get x is equal to -1. Okay. So the vertical asymptote occurs at the value of x that's not in the domain function. And remember, the equation of the vertical asymptote is the equation of a vertical line. Vertical asymptotes are vertical lines. Horizontal asymptotes are horizontal lines. Okay. All right. Equation of the horizontal asymptote. Well, you'll notice that the numerator of a rational function is degree 2, and the denominator of our rational function is degree 1. Okay. And so flipping back to page 3 of your handout, okay, where it talks about the asymptotes of rational functions. Remember, there were 3 different situations we had to be concerned with. In this case, right, the degree of the numerator exceeds the degree of the denominator. And when that happens, we call that top heavy. And when it's top heavy, there is no horizontal asymptote. Okay. When it's top heavy. So back on page 5, okay, you just write none. There is no horizontal asymptote. But going back to page 3, we have the special case where the degree of the numerator exceeds the degree of the denominator by 1. Okay. And when that happens, there is what's called a slant asymptote. Okay. And the equation of a slant asymptote is the equation of a straight line. So in the graph of this rational function, we have a slant asymptote, okay? Because the degree of the numerator exceeds the degree of the denominator by 1, okay? Now, so we have to find the equation of the straight line. We have to divide the numerator into the, we got to divide the denominator into the numerator. We have to divide the numerator by the denominator to get the equation of the straight line. Now in this case, there are two ways we can do that division, okay? Because this is linear in the denominator, right? This is a linear polynomial in the denominator, okay? So the first way I'm going to do it is by long division. Divide the numerator x squared minus x by x plus 1. Okay. You know how to do long division. How many times is x going to x squared? X squared divided by x is x. So x goes in x squared x times. And then you got to multiply x times x plus 1. And we get x squared plus x. And then that's subtracted from the dividend, okay, under the long division symbol. And when you do that subtraction, x squared minus x squared is 0. Minus x minus x is minus 2x. And you notice there's no constant term, right? This is plus 0 out here. Now x goes into minus 2x minus 2 times. So we have x, so we put the minus 2 up here. And then minus 2 times x plus 1 is minus 2x minus 2. And when we subtract minus 2x minus 2 from minus 2x, we get plus, the remainder is plus 2. Right? So the quotient here is the equation, okay, is the right-hand side of the equation for the slant asymptote. The equation of the slant asymptote is y equals x minus 2. That's the equation of a straight line, okay, in slope-intercept form. Slope is 1, the y-intercept is minus 2. Okay. Now you could also got that quotient, right, doing long division, or not long division, synthetic division, okay. Minus 1 would go in the box. Coefficient in front of x squared is 1. Coefficient in front of x is minus 1. And and there's no constant term, so you gotta have a 0 for the constant term. So you bring the 1 down. Minus 1 times 1 is minus 1. Minus 1 is minus 2. And minus 1 times minus 2 is plus 2. And 0 plus 2 is 2. So the remainder is, from the synthetic division, the remainder is 2, just like it was over here for long division. And so our quotient from synthetic division, minus 2 is the constant term, and 1 goes with x. So we have x minus 2, right, is the quotient, which is the same as the quotient from long division. So the equation of slant asymptote, right, is the equation of a straight line, right, y equals x minus 2. Okay. So minus 2 is the y-intercept, right? Here's the x and y axis. Minus 2 is the y-intercept. And it's got x equals 2 is the x-intercept. Right, it's got a slope of 1. So we can draw a dashed line that is the equation of the slant asymptote, y equals x minus 2. Alright, so on the right end, the graph is going to go up and to the right along this slant asymptote, either above it or below it. And on the left end, it's going to go down, okay? And to the left, either above or below that slant asymptote. All right, to get the x-intercepts, okay, you set the numerator equal to 0. Solve for x. And we get x is equal to 0. X equals 1 are the x-intercepts. So x equals 0, or the point 0, 0. X equals 1, or the point 1, 0, are the x-intercepts. Okay. So we can plot those, right? Here's the origin, 0, 0. Here's 1, 0. So with this slant asymptote, the graph, right? The graph must go up and to the right along this slant asymptote. It's above the slant asymptote, not below. Okay. The y-intercept is equal to f of 0. And f of 0, right? Using this form of f of x, you can see 0 squared minus 0 is 0, right? So we just get y is equal to 0. And so the y-intercept, right, is at the origin as well. All right. Oh, I forgot to draw the vertical asymptote. So here's the vertical asymptote, right? X equals minus 1, right? The vertical line. X equals minus 1. Okay. And we can reasonably deduce, right, that the graph is going to go up to the right of the vertical asymptote. But if we evaluate it at minus 0.9, it's just right at minus 1. And f of minus 0.9, you plug in minus 0.9 into either of these forms of f of x, and you get f of minus 0.9 is equal to 17.1, which is positive. So it does go up to the right of the vertical asymptote. And then it crosses the, goes through the origin, and then curves back up. And gets closer, right? And goes along the slanted asymptote and gets farther out you go to the right, the closer the graph gets to the slanted asymptote, right? That slanted line, y equals x minus 2. To see whether the graph goes up or down to the left of the vertical asymptote, I use minus 1.1 as a test point. And I got minus 23.1. So that means that the graph goes down to the left. Okay. So it means, and then it's also, we got the slanted asymptote. So the graph goes down to the left of the vertical asymptote, and then it's got to go up and form a turning point, and then follow the slanted asymptote going down to the left. Any questions on that? So that's what slanted asymptotes look like. Any questions on that? Okay. Graphing irrational functions was on the final exam last semester. So it's important that you understand this, how to graph rational functions. Okay. So no questions. Let's move on to E. Another rational function. Okay. And again, we got a factor. Make sure there are no common factors in the numerator and denominator. And the denominator factors into x minus 2 times x plus 1. The numerator is x plus 1. So we have a common factor in the numerator and denominator. So again, define the domain, set the denominator not equal to 0 and solve for x. Okay. So we have x minus 2 times x plus 1 can't equal 0. And when we solve for x, we get x can't equal 2, x can't equal negative 1. So the domain in interval notation, minus infinity, minus 1 parentheses, union, parentheses, minus 1, 2, parentheses, union, parentheses, 2, infinity. Do the range last. Now, define the equation of the vertical asymptotes. You have to cancel out the common factors first, right? X plus 1 is a common factor. So when we cancel those out, we're left with 1 over x minus 2. And this is called reduced form. Okay. And now with reduced form, you find the equation of the vertical asymptotes. So the denominator equal to 0, solve for x, get x is equal to 2. So the vertical line, x equals 2, is a vertical asymptote. What do we have at x equals minus 1 that we're not including it as a vertical asymptote? What's going on in the graph at x equals minus 1? We have a hole in the graph. Okay. And we learned that from page 1 when we did that. Oops. When we did this example on page 1. Okay. We had a common factor in the numerator and denominator. Right? We learned there was a hole. All right, for the horizontal asymptote, you'll notice that the numerator, right, in our original function is of degree 1. Separate upper example from lower. And the denominator is degree 2. And so when the degree of the denominator exceeds the numerator, what do we call that? Bottom heavy. And when the rational function is bottom heavy, what's the equation of the horizontal asymptote?
Y equals 0.
Yeah, y equals 0. So the horizontal line, y equals 0, and the x-axis coincide. Okay. And so our horizontal asymptote, right, is the x-axis. X-intercept, 1, right, so you go with reduced form, okay? 1 secant equals 0, okay? So there's no x-intercept, okay? The y-intercept doesn't really matter whether you use the original function or the reduced form. Y is equal to f of 0. And again, when you put 0 in for x, right, all the terms with x in it are equal to 0, and you just left the constant term in the numerator over the constant term over the denominator. So we have 1 over minus 2, which is minus 1/2. So the y-intercept is at y equals minus 1/2, or the point 0 minus 1/2. So we can plot that point. Here's minus 1/2 on that y-axis. So I suspect that the graph goes down to the left of our vertical asymptote. All right. There's a hole in our graph at x equals minus 1, right, from up here. And to find the y coordinate, you put in minus 1 in for x in reduced form. So the y coordinate is equal to 1 over minus 1 minus 2, which is equal to negative 1/3. So the hole is at the point minus 1 minus 1/3. That's the x and y coordinates. Oops, sorry, for the hole. So here's minus 1 on the x-axis, and then minus 1/3 is just below the x-axis. And it's just a little higher than minus 1/2, where the y-intercept is. Okay. So you got to draw the hole a little higher up than the y-intercept. All right. So to the left of the vertical asymptote, does the graph go up or down? So 1.9 is just less than 2. So when I evaluate the function x equals 1.9, it's usually easier now to use the reduced form than the original form, right? Either of these two forms in evaluating the function. Okay. And when you plug in 1.9, okay, you get, I think, I didn't actually evaluate it, I just looked at it. 1.9 minus 2 is negative 0.1, and the reciprocal of negative 0.1 is negative 10. So the graph goes down to the left of the vertical asymptote, which we expected. We were anticipating that was going to be the case. And the x-axis, or the horizontal line, y equals 0, right, is a horizontal asymptote. So we expect it to flatten out, going to the left, just under the x-axis. Okay. It actually gets closer to the x-axis the further up to the left we go. To the right of the vertical asymptote, 2.1 is to the right, just to the right of the number 2 on the x-axis. So f of 2.1, right, is equal to plus 10. When I put in 2.1 in for x up here, 2.1 minus 2 is 0.1. Reciprocal of 0.1 is 10. And so the graph goes up. Okay. So f of 2.1 is equal to 10. So the graph goes up to the right of the vertical asymptote. You got to draw it halfway. You can see. And the x-axis of the horizontal line, y equals 0, is a horizontal asymptote. So it comes down and flattens out to the right above the x-axis. Okay. The last thing to do is the range. Okay. And so looking at the graph, okay. So did everybody get everything on the bottom? Okay. There's no minimum y coordinate. And on this part of the graph, the y coordinates exist for all real numbers until we get to where the open hole is. And the hole has a y coordinate of -1/3. So -1/3 is not in the range of this function. And the horizontal line, y equals 0, is a horizontal asymptote. The graph doesn't touch it, right? Doesn't cross it anywhere. And so 0 is not in the range. Y equals 0 is not in the range. And for this part of the graph is completely above the x-axis, right? And all the y coordinates are greater than 0. So for that part of the graph, the range is 0 to infinity, x, y greater than 0. And that is the range, right, from the graph of this rational function. Any questions on that, ladies and gentlemen? Okay. Again, I want to emphasize graphing a rational function was on the final exam last semester. Okay. All right. In this last example, we got to sketch the graph of a rational function that satisfies all the following conditions. F of x increases without bound as x approaches 1 from the right, and f of x decreases without bound as x approaches 1 from the left. Okay. So if x is going up to the right of x equals 1, and f of x is going down to the left of x equals 1, what does that make the vertical line x equals 1? It's the vertical asymptote. So here's the x-axis, here's the y-axis. And to the left, to the right of that vertical line, right, graph is going up. And to the left of that vertical line, the graph is going down. Then we might modify our drawing a little bit, okay? But that's what we have for now, okay? Then we're told f of x increases without bound as x approaches -2 from the left, and it decreases without bound as x approaches -2 from the right. So here's -2 on the x-axis. So f of x increases without bound as x approaches -2 from the left. So that means the graph is going down to the left of -2. F of x, you know what, I drew that wrong. F of x is increasing without bound as x approaches -2 from the left. So It's actually going up. Sorry about that. F of x decreases the left bound as x approaches -2 from the right. That means the graph is going down to the right of x equals -2. So that makes the vertical line at x equals -2 a vertical asymptote. Again, we might tweak the drawing, just laying things out. Has a horizontal asymptote y equals 0. So again, that coincides with the x-axis. So the x-axis is horizontal asymptote. So we might expect that this graph here, right, this part of the graph is going to flatten out, going to the right, above the x-axis. Okay. Never crosses the x-axis. So that means, right, the graph never crosses the horizontal asymptote before flattening out, going to the right or the left. Okay. As a local maximum at -1, -2. So here's -1, x equals -1. Here's y equals -2. Okay. So local maximum is the top of a hill. Okay. And when you guys, those of you who have to take Calc 1, right, you'll terminology like local maximum, local minimums, right, you'll hear that a lot. So, since the x-axis is a horizontal asymptote and the graph doesn't cross the x-axis, it has to come down and flatten out to the right in that part of the graph. It has to come down and flatten out to the left in that part of the graph. Okay. And since -1, -2 is the top of a hill, you draw that part of the graph with the point -1, -2 at the top of the hill for that part of the graph. We're done. We have successfully, right, drawn a function that meets these conditions, a rational function meets these conditions.